Hi! In the next few days, whenever you happen to see this, whatever group you're in, we'll learn a little bit about periodic table and how it's put together and where things are. And you'll probably hear the words metal and non-metal. So I kind of wanted to give you a rundown of what that means, what the difference is, and how they behave, and why we care. And then also tell you a little bit about valence electrons here at the end of this video, and try to work in some other definitions as well. I thought it'd be easier for me to have all the words written out first. Of course, I'll share this notability with you. I think it might be better for you to handwrite them out. Your brain makes connections when you write words. It helps you remember things. But of course, you guys know better than me. You're all-knowing teenagers, so you do what you got to do. But I'll go through some of these words here and tell you a little bit about metals. So most of the periodic table is metals. About 3/4 of it is metals. So most of the element are metals, and almost all of them are solids at room temperature, and except mercury is an example that's not, but many of them are. And metals are unique because they are malleable, which means you're able to bend them or shape them into things like aluminum cans or other, like, for example, phones, cases, things like that. They're very easy to do. That's why we like metals, pots and pans. You can shape them very well. One other thing about metals is that they're ductile, which means you can pull them or stretch them into wires. This is why copper is used almost for every single wire in your house, especially for electricity. Copper is used for internet cords, for electrical cords, for the wires inside your house that you can't see. All of that is copper, and so that property is called ductile or ductile, depends on how you pronounce it. Anyway, and then you might probably already know, but metals also conduct electricity and heat very well. This is why another reason that copper is used, or metals are used to carry electricity in your house. This is why metals are used for like pots and pans in your house, because they conduct heat very well. They take the heat from the flame and transfer it directly to your hamburger or whatever. Non-metals, on the other hand, are basically opposites. So they have some are the solids, but most of them are gases at room temperature. Non-metals are the upper right-hand corner of the periodic table, which I'll show you in just a moment. Metals, when you hit them with a hammer, metals tend to flatten out and not break. But for non-metals, the ones that are solids, they'll break when they're hit. You can think of graphite as a really good non-metal. It's a good example of what most non-metals look like. They're dull in appearance. They break very easily. So the graphite in your pencil, the graphite in your, we call it lead, but graphite's really carbon. And so that's a non-metal. So they're brittle. They don't conduct electricity very well or heat very well. They are, like I said, kind of the opposites of metals. And on the periodic table, right here, they're sort of cut in half, and you're going to have an activity where you do the real, where you really label them, but I'll just give you a sense, like all of this is metals, all of these are metals, and for non-metals, you have all of these here in this corner, kind of like that. And I'm missing some, it's not exact. I'm just kind of sketching the in-between section in the middle that I've not colored. Those are called metalloids, or sometimes they're called semiconductors or semi-metals, because they have properties of both metals and non-metals. But as you can see, the periodic table that I've colored here is mostly green. That's because most of the periodic table is metals, as I mentioned. Only a very small percentage of the periodic table is non-metals. That's the orange part there. Okay, we'll come back to that. Actually, we'll continue with it. Why not? So one thing that I'm just going to erase because this is not what we're looking for here. When we're talking about things in the periodic table, one thing that's good to know is you have some shorthand to say what is what. And so all these columns here, the up and down, those are called groups. And you could probably label this on your periodic table, or you could just write it down in your notebook. And all of the horizontal rows, like here and here, all of them, those are called periods. The groups and periods are numbered, so you can see that here. In the groups, they have this 1A, 2A system. I usually just go 1 through 18, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There you go, oopsies. That's 18 different groups in the periodic table. And these what you'll learn about, these interior transition metals, they actually go right in there. But that pushes the whole periodic table out off of this piece of paper, so they take those out and they put them down there. This is a common thing to do in most periodic tables. I want to erase some stuff here. The ones that are tall columns, these guys here are tall groups. These are called the main group elements, or the representative elements. Representative elements are called that because they represent all the kinds of things that you'd find on the periodic table. You've got metals, you've got nonmetals, you've got solids at room temperature, liquids and gases, high densities, low densities. So the tall columns are sometimes called representative elements or the main group elements. So I wanted to point out that word, the definition to you. And then finally, if we scroll back up, one thing that's important about how chemicals interact that will kind of set us up for the next unit, which will happen sooner than you think, are valence electrons. And the reason that we care about valence electrons is because they're the ones that are involved in all chemical reactions. And the valence electrons are the ones that are in the highest energy level. You can identify valence electrons two ways. And if we have written out a, let's say, electron configuration, let's say it's this one, 1s2, 2s2, 2p4. Actually, let's keep going. Let's call this 2p6. Make our lives just a little bit easier. 3s2. The energy level is the biggest number, or the big numbers, all the ones I'm just pointing to right now. That's the energy level. And so the electrons in the highest energy level are the ones at the biggest number. So this is 3 is the biggest number, and we have 2 valence electrons there. So 2 valence electrons for this particular atom. 3s2 is magnesium, right? Right here. Yep. 1, 2, 3. 3 down in the S section, 2 over, that's magnesium. So magnesium has 2 valence electrons, and you can write out the configuration for all of them like that to find valence electrons, but it's far easier to use this shorthand, which is just count the column it's in. You only count the tall columns. You do not count the middle columns. We hate them. They're so dumb. So it's 1, 2, 3, 4, 5, 6, 7, and 8. This is the valence electrons for each of the atoms in a particular group. So all the atoms in this group have 1 valence electron. All the elements in this group have 2 valence electrons, and so on and so forth. It makes your life a little bit easier when you have to calculate valence electrons, which I'll be doing later. So why do we care? Well, the reason that we care is because elements in a group, let's start the column, right? Elements in a group have similar properties because they have the same number of valence electrons. So for example, all of, let's say, these react, and these guys all react very violently with water. And the reason that they do that is because they all have 1 valence electron. And what they're doing, which we'll get to next unit more in depth, is they want to have 8. Okay, some elements are very stable. The noble gases are very stable here. These guys do not react with many compounds, and almost none, in fact. And the reason that they don't react is because they have a full set or full shell of valence electrons. So that provides some stability for that atom, and that helps it not react with things. So if you take anything away from it, it's how do you calculate valence electrons, and the best way to calculate valence electrons is simply to count what column it's in, only count the tall columns. You can also, if you'd rather, write out the configuration and then see the valence electrons that way. One thing I should point out, though, is that if we did take one more thing, like let's say 1s2, 2s2, 2p4, 1s2, 2s2, 2p4, of course, is oxygen. And so one way, if I asked how many valence electrons was that, you could say, oh, well, it's right here. So it has 6 valence electrons. However, You can also add up this way. Remember, it's the largest energy level, and here we have two twos. The 2 is obviously the largest number. It's bigger than 1. So you count all of the electrons in there. So for this one, you've got 2 electrons there and 4 electrons there. You total them up, and that's how you get 6 valence electrons. I'm not going to fit valence in there, but you get the idea. So once again, calculating valence electrons, differentiating between metals and nonmetals by their properties, and then a couple of definitions here on what we call periods and groups. This has been super fun, and I hope you enjoyed yourselves, and can't wait to see you again. Okay, bye.